My name is Jennifer Jacobs. I'm an assistant professor at the University of California, Santa Barbara. I'll be presenting our paper entitled Throwing Out Conventions, Reimagining Craft-Centered CNC Tool Design Through the Digital Pottery Wheel. This paper is co-authored by Ilan Moyer at MIT and Samuel Bourgault and Devon Frost, also at UCSB. Many current non-industrial digital fabrication tools reinforce the conventions of industrial CNC machines. This is especially true for personal fused deposition modeling 3D printers, which, despite being employed in radically different scenarios and use cases, share the primary mechanisms and principles as those used in industrial CNC technologies. Digital fabrication technologies that are compatible with traditional craft materials still require fundamentally different forms of interaction than manual craft. We built from our existing expertise in clay 3D printing to examine the differences between digital fabrication technologies for clay production and traditional clay tools, comparing a clay 3D printer with a traditional pottery wheel. The wheel is a very old technology with widespread contemporary use. To use it, a craftsperson throws a piece of wet clay on its head and manually shapes the material into a vessel as the wheel rotates. Clay 3D printers use the same clay as those on pottery wheels, but in form and function, they have more in common with 3D printers that use plastic than pottery technologies. This is because developers have transposed the apparatus of plastic 3D printing almost verbatim in clay 3D printing technologies. Although there are benefits to established CNC printing machine architectures and workflows, continually reapplying industrial conventions for novel digital fabrication technologies can lead to pushing design patterns where they may not fit. In an effort to push CNC technology design in productive yet novel form factors, we imagined an alternative reality in which clay 3D printing grew out of tools from manual pottery production. We used this premise to pose 3 research questions. First, what form and mechanical architecture might a clay 3D printer take to reflect the conventions of ceramic tools? Second, how might ceramic artists perceive a clay 3D printer that looks and feels like a manual tool? And third, what alternative practices and products might emerge from the adjacency of manual and digital ceramic mechanisms in a single tool? The result of our study was the Digital Pottery Wheel, or DPW, a ceramics throwing wheel with clay 3D printing capabilities. To develop the DPW, we informed engineering decisions with the ethos that we were building a pottery wheel first and a 3D printer second. We prioritized the form factor and operation of the wheel over established CNC mechanical design precedents that optimize the machine and reduce cost. The digital pottery wheel consists of a polar coordinate mechanical architecture. The wheel head simultaneously serves as a wheel, build platform, and angular positioning mechanism. We cantilever the extruder over the wheel with a horizontal swing arm which is mounted to the vertical z-axis. Radial positioning is achieved by rotating the z-axis column, which causes the extruder to sweep at the end of the swing arm. Here's a figure of the mechanism we developed. Aside from repurposing an existing clay extruder, we fabricated an entirely new mechanical architecture. We selected transmission elements and stepper motors that would allow us to maintain parity with the wheel speed and output of output power of high-end throwing wheels. The DPW represents the first polar coordinate clay 3D printing machine architecture and one of a very few number of polar coordinate 3D printers that exist today. We developed a modular control system to prototype real-time, automated, and manual interaction modalities on the wheel. Our control system differs from that of existing CNCs. For traditional CNCs, motors are driven by CNC controllers that convert G-code commands into a synchronous stream of step and direction pulses. This signaling scheme contains real-time information about each motor's state, but G-code controllers do not expose these signals as data. We reconceptualized these signals as synchronous motion streams and designed the DPW control system as a series of modules capable of transmitting and modifying these streams as first-class data. We use a centralized machine controller module to maintain machine state by assuming centralized control over the motors and limit switches. We then use interchangeable modules that can be chained for composable behaviors. We created a module development firmware centered on streaming and modifying step and direction signals as the primary data type. Our firmware enables us to flexibly mix multiple motion streams, whether they are internally generated, e.g. by a velocity-based generator, or sourced externally, for example through a knob or a pedal. We accomplish this by allowing each source to independently update the target position of a common output channel. To maintain the ability to work with standard G-code, the machine controller can accept the step and direction signals from a Cartesian G-code controller as inputs and convert these on the fly from Cartesian to polar space. This allows us to use existing technologies for CNC toolpath design in tandem with the wheel, and automatically 3D print forms with comparable accuracy and quality as existing clay 3D printers. We relied on a design evaluation series of sessions with professional ceramicists to interactively develop the interaction modalities of the DPW. We conducted 6 sessions with 9 professionals over 3 weeks. During these sessions, the professionals made artifacts with the wheel and shared their reflections. We iteratively developed and revised DPW functionality between each session. To show some of the initial interaction schemas that resulted from our design study, I'll first discuss manual throwing. We created a manual throwing mode to support standard skilled throwing practice. Flipping a physical switch on the wheel toggles the digital pottery wheel to throwing mode, which automatically moves the print item out of the way. All machine inputs are disabled except for the wheel, and the physical UI adjusts the pedal's velocity limit to allow the artist to bring the wheel up to a top speed of 250 rotations per minute. The wheel then functions identical to a standard pottery wheel. As I mentioned before, we also support conventional G-code printing. So flipping the physical UI switch back to the right causes the arm to reposition over the center of the wheel before enabling all inputs on the machine controller. Artists can engage in several different printing modes. Because we use a CNC G-code interpreter as input to the machine controller, an artist can upload Cartesian G-code and execute it automatically, as shown here. To support 3D printing without predefined G-code, we created mechanisms to control the printing directly. The wheel contains 4 physical user interfaces to facilitate real-time control over the digital pottery wheel's 4 axes. We use a traditional pottery wheel foot pedal to control the rotational speed of the wheel. We use a hand lever to manually adjust the position of the swing arm. And we attached a bank of controls on the left of the wheel that includes a knob that finally adjusts the height of the Z-axis carriage, a knob that controls clay extrusion rate, and a toggle switch. We use this interface to explore manual printing where an artist controls printing in real time. We created a pot assist module that maps physical UI elements to the digital pottery wheel axes while supporting automated layer height increase. Here we show an iteration of pot assist where the artist first starts in base mode and creates a base of the pot by manually moving the hand lever while spinning the wheel with the pedal to print a spiral base. Multiple layers can be created by using the Z baby stepping knob to raise the axis after one layer. When the artist is done building the base, they start and stop the wheel with the pedal to move into wall mode, where the Z-axis begins to raise at a rate proportional to the wheel velocity. In wall mode, the artist is free to move the lever to create undulating walls or any shape they want. To enable the duplication of manually printed designs, we created a recorder module that samples and records any inputs to an onboard SD card to reproduce manually produced forms. The artist enters recording mode by pressing the recording module's UI knob, and then during recording, the inputs are both sampled and passed through the module's outputs, enabling the machine to be controlled while being recorded. Here the artist is using recording while in the pot assist mode. The relative nature of motion streams allows the same recording to be played freely with different settings mixed in from the manual controls. The ceramic products created during our design study suggest that the DPW presents very different expressive opportunities than Cartesian clay 3D printers. Foremost, artifacts created with the wheel during our study show that it is possible to create forms that would not be feasible with a 3D printer or a wheel alone. These examples show vessels that mix thrown geometry with computationally generated G-code and manual variation in the printing process. Furthermore, our study provided evidence that the DPW changes perceptions and engagement with skilled manual ceramics. To provide one example, one of our participants, Linda, had arthritis in her hands that had prevented her from throwing. She perceived the DPW as a potentially assistive technology that would enable her to throw again by using the printing mode to fabricate basic pre-centered cylinders that she could then manually manipulate without the physical labor of manual centering and opening. These images show 2 pots Linda threw in the wheel during the study. While it is premature to make any claims about the DPW with regards to accessibility, Linda's experience demonstrates how re-envisioning CNC machine form factors can change the ergonomic qualities of the interaction and the perceptions of the practitioner. Overall, our research reinforces the idea that by understanding traditional makers, we can develop innovative and impactful computational technologies. We found that reassessing established technological paradigms through non-digital fabrication tools can generate novel insights for CNC technology. Furthermore, bringing the technical expertise of artists to bear in CNC interaction can reshape perceptions and practices in 3D printing. We encourage you to see our paper for additional findings in detail. In conclusion, I would like to thank my co-authors and all of the artists who participated in our design study.